All right, we made it to the last day of review. I want to compliment you guys. I think almost everyone's done a really, really great job of going back and fixing their work as they go. So I'm sure it's annoying to get to one day's work and have to circle back, but I'm really proud of you guys for working so hard this week. For statistics and probability, this is always a tricky unit because it's something that a lot of times you only kind of get to at the end of the year, and then it's June and we're not working too hard or paying attention. So for statistics and probability, it's okay if you don't remember a lot of this from last year. A lot of it's really logical, and it relies on ratios and proportions. For the first 10 cards numbered 1 through 10 are mixed together and then one card is drawn. Find the probability of each event. So this notation, P with parentheses, that means the probability of, what's the probability of drawing a 7? It's going to be out of 10. Well, how many cards could possibly be labeled 7? What's your probability? For number 2, it's still working with 10 cards. And we want to think about the probability of drawing a card greater than 7. So what's the probability of drawing an 8, 9, or 10? For the next couple, use the fundamental counting principle. That might be language that you don't remember. It says to find the total number of outcomes in each situation. So the fundamental counting principle pretty much just says multiply all the possibilities to find the total number of outcomes. For number 3, choosing 5 flavors and 2 sizes of juice, 5 times 2. For number 4, tossing 4 coins, you have 4 coins and you want to think about what are the possible outcomes for each one of those to find the total probability. Let's say for problem solving, I know that these have been trickier. Today I don't think they're too bad. Number 5, a survey showed that 60% of students would select bumper cars as their favorite ride at an amusement park. Out of 4,000 students, predict how many would select roller coasters as their favorite ride. First of all, if it's only 60% of 4,000, you know it's going to be less, and otherwise you're going to be setting up a proportion just like you've done earlier in the week to say that if you know 60%, 60 out of 100, how many students are going to be selected from all 4,000? Number 6 is another one you might not have seen or remember that language, but I think you can use logic to sort it out. It says, Mr. Jennings put student names in a hat and selected 4 names without looking. What type of sample did he form? So for this one, I want you to use context clues and take your best guess. Does that sound biased? Like a convenient sample? Is it convenience? Is it simple and random? Or is it systematic and random? If you want to look them up, you're welcome to. But for this one, I'm okay with you just taking your best guess. For number 7, Roger wishes to determine the average high temperature for any given day in his city. To do this, he records the high temperature for every day in December, January, and February. He then adds the temperatures together and divides the sum by the number of days in his sample size, so he calculates an average. Explain why his data would not provide relevant results for what he was trying to accomplish. So for this one, I'm not looking for a number. There's no x equals, there's no percentage. You're just trying to say, where did he go wrong? If he's trying to find a way to find the average temperature for any day in his city, where did he go wrong with his experiment? Number 8, you want to read carefully. It's kind of tricky. A laundry basket contains 8 white shirts and 6 black shirts. What's the probability of randomly picking 2 black socks from the basket? So for this one, you just want to think, are there any socks in the basket? And what would that look like as a probability or a percentage? How likely could you be to pull black socks out of that basket?